logic. And so when you see a lot of state and a lot of logic, you ask yourself, well, can you program that and that alone? And the answer is a resounding yes. So as we hope to demonstrate. So, we need a slogan, as if we didn't have the most enthusiastic introduction ever. So, stealing from Arthur C. Clarke, any sufficiently advanced or complex input data or metadata acts as bytecode to the system that must interpret it. The system acts as a virtual machine for that bytecode, comrades. I quite like the cat. The words say, to the winner of the all-union socialist competition. I don't know what the competition was in. Okay, so we're going to stick to the slogan, and we're first going, and you may have seen that slide in our previous talks. This is your code, and it sort of reaches down, pulls up bits and pieces of your data, and pushes it through its tubes, and does its Lovecraftian tentacled thing, puts them down. There are many flows going through the code. And among those, there are all sorts of bugs, features, buffer overruns, and so on. It's really like a virtual machine working on that tape. So, to remind you of our previous effort, which showed this, which demonstrated this with ELF ABI, Rebecca Shapiro did that. I hope that she would be able to hop on the stage today, but she is otherwise engaged. So we're going to do a 3-minute version of what she did. Think of the RTLD. Consider the RTLD. Here's your dynamic linker, or the dynamic linker. And what it does is it treats your program as a tape. When it loads it, it may choose to load it at a different address. We know this as ASLR in the recent world. And prior to that, we knew it as relocation. So there are some tables, there's some data that the code reads. And there are places in the code that the code writes. And when you have something that reads and writes, well, they could read and write to the same place, right? And this could be your tape of your Turing machine, of your automaton. And indeed it was. And if you think about it, what the RTLD does is that it rewrites the program rather thoroughly. It takes up addresses of relocation entries, offsets into the program, and depending on the type and symbol, it rewrites the absolute addresses or any other addresses that need to be patched. Okay, so how does it do that? If you look at how it rewrites them, and there are quite complex tables of operations, this is a whole lot of arithmetic. So your relocation entry has the type that is really like the bytecode of a virtual machine, with memory copy and addition. And when you have arithmetic, then all you're missing is branches and loops. And it turns out that you can, by overlaying these structures, the symbols and the RTLDs, and by patching not just code, but those structures as such, the reading and writing trick, you can actually do anything you like with the memory of your program while it's loading. And I encourage you to look at that. And this is available as ELF. We implemented the brainfuck compiler. So Bex, who is now known as .bx for the ELF section, for the special ELF section. She gets her own after this amazing cool work. Look at that. So now we're going to do the same thing for something else. And this is a good place to mention quite a few of the inspirations that put us on to binary formats as such. Binary formats, other tricks, and so on. And we're going to see a few more of these. These are the ELF inspirations. K-log, the Grog, Silvio Cesare, the early pioneering work in Frac, Mayhem, and then Aresi team. Aresi project is live again. If you're interested in ELF, do your look at your Aresi project website. And Locreate, which showed us the trick of using the relocation entries in interesting ways. Okay. Now, one day, I am relaxing with, some Lefroy, and the Intel manual. They are perfect companions for a relaxing evening. And this thing, PFLA, jumps out at me. And I think this is the Page Fault Liberation Army. Okay, it's actually page faulting linear address. But, as they say, think of this world with fantasy added or something like that. With add imagination. Who is this guy? We measure our light bulbs after him. Yes, this is James Watt, the inventor of the steam engine. So if you see, he was berated in his youth for being idle and hanging around things that put off steam. Okay, so we're going to build an engine and take it as far as it can go. This is somewhere in Siberia. I don't know if you can enjoy it fully. We do have limitations. And maybe, somebody else would join us and help us build the snow plow. This is the snow plow. This is how high up the snow flies as that thing drives through the snow, somewhere in Canada. Okay. All right. And the reason we do this is that we want to know what computers really are. I just keep quoting myself, but this is the community, this is the situation that I truly believe carries on what Church and Turing did for traditional architectures. What they did with theorems, we do with exploits. We show what's really there. We show what computational power is really there. The actual computer, not the one of developers' dreams or nightmares. And so, first I'm going to tell you a little white lie. We're going to talk, just look at this situation, right? Here is the MMU. The MMU translates every address that you're issuing, and it's driven by data. So the interrupt descriptor table, where you have the address, the offset of the handler that will be called for a page fault handler or other exceptional conditions. The global descriptor table that describes the layout of memory in the terms of Old Republic, of old segmentation system, going to gone in x86 and 64, but still there for 32, and page tables, which actually drive the translation. Somewhere on the side are the TLBs. We ran out of boxes while making this picture. And what happens when an address translation fails? A page fault handler is called, and that page fault handler will write some information onto the stack. That is to say, into the memory, into RAM, where it thinks the stack is. Now, hang with me. What if the stack is where the page tables are, or where the IDT, GDT are, or like somewhere overlapping with them in interesting ways, right? And the answer is yes. This is your tape. This is your tape. This is your Turing machine. In fact, the MMU has enough. I mean, this is our state. We will use the memory rights of the MMU to the regions that control the logic of the MMU. And then, this will unfortunately be a little bit more complicated than just overwriting page table entries, but it will work. And you'll hopefully see a demo. So, and of course, then the question is, why do this? Well, we're going to intersperse the discussion with the examples of inspiring research. Absolute lead among these is the PAX, GRSec PAX kernel hardening patch, because it does really interesting things with memory. It's the virtual smorgasbord of clever techniques, and then we'll lead up to how this actually builds. Okay, so think tentacles, think Yog Sothoth, or any Lovecraftians here? Yeah, well, if not, think strange entities from out of space that are made out of tubes and have interesting control flows and data flows inside them.
And to repeat, we can get really fun things if we happen to make various data structures align in weird ways. And we weren't the first people to do creative things with page tables. Before us, as Sergey has mentioned, there have been many other hacker projects that have tried to do interesting things that Intel didn't think they could do, that you could do with their awesome hardware, by cleverly manipulating various structures. And in order to understand the work that we've done, I'm going to have to get a bit boring, as Germans always do, and dryly go through the descriptions of various tables in the processor. But so that less than half of the room falls asleep, I'm going to interject it with fun comments about all the things that good neighbors in the past have done, and all the fun tricks that you could potentially do that might be a little less white-hatty as well. And so let's get started on this wild roller coaster ride of the fun stuff that is buried deep in the Intel manuals, which I encourage everyone to read over a good glass of scotch.
Enjoy responsibly.
The manuals. Okay, let's first take a step back to the good old days of yore, when everyone thought that 16 bits of address space was good enough and DOS was considered a fancy operating system, because who needs that? Back then, the way you would do virtual memory was through an amazing concept called segments that has now fallen out of use. The idea behind a segment is that you have a tagged range of memory. You say, this is a range of memory that is a beginning and a size, and it's supposed to be used for this purpose. This is supposed to be a stack, or this is supposed to be code and data, and you can say, I want to use this data region for the stack, I want to use this other data region for my heap, I want to use this for my thread local storage, and so forth. And importantly also, that means you can have a different code path to fetch instructions and a different path to fetch data, which wasn't reintroduced in modern paging systems until 2004 when Intel added the NX bit. And these segments live in, at least in 32-bit mode, it's completely different in 16-bit mode, in a table called the global descriptor table, which just contains this type information, the base address of a segment, and the limit. And what the processor does on every memory access is that it looks up the segment, finds its base address, checks if it's less than the limit, and then proceeds to let the access either pass or trap it.
And think about the worth of this. All bytes are created equal. You don't really know your data from your code, and vice versa. That way, you can impose annotations on wide ranges of bytes and say, okay, it's this object that's been loaded in here. And that was the idea of tagged architectures. And then it got de-emphasized and de-emphasized and de-optimized, and it's on its way out in x86-64. But that's how it worked.
Yes. And while this was mostly used to do multitasking in DOS, and people were never really happy with it because it wasn't compatible with the C abstraction of having a single address space, in 1999, Solar Designer, who is also quite famous for a few other tricks, looked at this and decided to use it to prevent the, at the time, very common exploiting technique described in, for example, stack smashing for fun and profit, which was just that you write some shell code, send it in, cause a buffer overflow somewhere, and then just immediately have the code return to that shellcode that you have on the stack. He did this by, typically at the time, all operating systems set up all the segments to be identical with a base of 0 and a limit of 4 gigabytes, which just meant that the entire segmentation mechanism had been disabled. It just did the identity transform in every address that was passed through it. Instead, he just did the one little change that he changed the code segment for user space to have a limit of 3 gigabytes minus a little bit of space for the stack, so that whenever you had a data access, it would just sail right through the segmentation logic. But if you had a code access that was going into either the kernel or into the stack, that would cause a trap into the operating system, which would then check what the last instruction executed was. And if that happened to be just a specific return, it would detect that someone is trying to do a return into stack code. It's probably going to be bad. If someone jumps into it explicitly, this means they're implementing some crazy JIT or something, then we should maybe let it go through, because they really didn't want to break any legacy code. It then turns out that GCC actually creates code that returns to the stack, so they added a few exceptions to detect those specific trampolines, and so the actual code is not as pretty as you would expect it to be, but such is life, and it was fairly efficient at completely blocking the very basic stack smashing for fun and profit attack, and suddenly you had to find a heap overflow instead of a stack overflow.
So page fault handler is probably the most overloaded bit of the IDT for trying to enforce policy. I mean, this is policy, right? You don't get execution on the stack unless you are one of the special cases. There are many more. We'll cover some more. But it's just amazing how this stacking of nifty tricks has happened on top of that diligent worker that is the hash PF.
And as I mentioned, this segmentation mechanism, which was used here, has been somewhat de-emphasized. What modern operating systems actually use to implement virtual memory is the paging system, which is still used to this day. I'm just going to give a simplified overview of it as it was about 10 years ago. By now it's become more complicated, but the same basic principles still apply. You take your linear address, that is the pointer that you have in C, and split it up into 3 parts. The highest 10 bits, then the middle 10 bits, and then the lowest 12 bits. The highest 10 bits go to used as an offset on top of a control register in the processor, where you find a page global directory, which contains a pointer to a page table. You add the second part of the virtual address to that page table address, and in there you find a page table entry, which just contains a physical page number in virtual memory, or in physical memory. And that is the physical page that your virtual access then goes to. In addition to that, the page tables contain some permission bits. Initially, there was just the present bit, which is used to signify that this page is actually live in RAM and you have already allocated this memory and it's not currently being swapped out to disk somewhere. Then you have a page to distinguish kernel memory from user space memory, and you have another page to distinguish, or another bit to distinguish read-only memory from read and write memory. Afterwards, about 15 years after this was first implemented, Intel also added another bit to signify if this was code or data. That is the NX bit to prevent execution from a page. But as it turns out, they already had the mechanism to implement this NX bit in the silicon. And you could, in fact, implement it without the explicit hardware support given through that bit.
So observe, there is this one register, CR3, and your entire view of memory is controlled by it, as well as by some other things, as we will find out. But it's really the thing that completely changes your world, and by pointing you to a different page table, when you change its value by your typical move. This is the context. This is absolutely the control on top of your world. That's one thing to observe. The second thing to observe is that in your page table entry, well, you can see there are quite complex structures. There are bits that cause trapping, that cause the page fault handler or the double fault handler, in certain circumstances, to get called when they are set right, when they are set right. So this is your opportunity to drive that logic by setting those trapping bits in the page table. And you can think of them, I think of them, as tags that labels on the objects in memory that are spread through the page table. It's the tag, it's as in the tagged operating systems or in tagged memory. It's just that it's smeared through your page tables in the form of these trapping bits. And PAX has been, as far as I know, the first to actually use them in that composite label trick. And so you've got these two stages, segmentation and virtual address translation, that one feeds into the other. And when something in this system, in this address translation process, is not according to the bits you set,
you get a trap.
It's a trap. All right.
And as Sergey has already mentioned, a project that really did a lot of things with these mechanisms before us, and that we owe a lot of inspiration to, is the PAX project, which is an awesome Linux kernel hardening patch that does a whole lot of things, and we're just going to focus on a few specific features of it, but you should really go check it out and see all the other things, because even though we might not have the time to explain them here, they also contain some pretty nifty tricks. And PAX did a lot of we're the first to implement a lot of things that we now take for granted in modern operating system security, such as the execute protection on x86 and things like ASLR. And to this day, the PAX ASLR implementation is one of the most complete that I've seen.
It is also the least cited bit of research into constructing x86 policy, which is sad. So, cite it, if that's what you do.
And PAX has two different, as I mentioned, PAX tried to emulate this, at the time, non-existent NX bit in the page tables, and they have two separate mechanisms to emulate it on 32-bit processors that have different drawbacks, and so because Sergey is such a big fan of PAX, I'm going to let him briefly explain it.
So the two mechanisms, the first mechanism used the segmentation register, the segmentation system. So you had the memory split into the available 3 gigabytes of user space. This was a user space trick, a user space non-executable address trick. It was split halfway, and one half of this was used as code and reference, so the other was used as data. And so when your instruction fetch happened, and remember, the x86 processor has two paths for extracting data out of memory. You can fetch data as instructions, or you can move data in and out as well, data. So your jump and your move will go through different paths of silicon, and will actually go through to different translation look-aside buffers as well. So you would send your instruction fetches to the upper half of your memory space, and you would send your data access path to the lower one. And it's pretty nifty. Unfortunately, it halves the available amount of your address space. Not that you could use 3 gigabytes so easily back then. But what's a lot more interesting is the other mechanism that they used, the page exec. Now, the page exec takes advantage of the TLB having its own logic. If you are, remember, there is this pretty big virtual address translation mechanism. So you look up from CR3, you look up one half of one part of the address, then another part of the address in another table, and there are 3 or 4 on modern processors layers of indirection. Okay, this is horrible because, of course, this is not how it works. Because you can't afford to do 3 memory references to look up a memory reference. So what happens is that there is a translation look-aside buffer, a cache, in which a virtual address looked up, that is to say its page table entry, observe the present bit, the read-write bit, the user supervisor bit. These bits, there are lifted up into the TLB. And if you are going the code path, it's the ITLB. If you're doing the data path, it's the DTLB. But that happens only if the address lookup is successful. Now, these TLBs are not synchronized with page tables at all. So you can flush the TLBs from your with an assembly instruction, but that's the deal there. So the user supervisor bit was used as the substitute for non-executable bit when the non-executable bit wasn't there. It's at the top of the enhanced page table entry for 64-bit systems. And that's the way it worked. You set the supervisor bit. I'll call it the user bit. You'll set the user bit in the TLB to trap on a data access. So we're looking at DTLB, right? And you set it to trap always in the page table. Now, when it traps, you check if the EIP is actually the address that you're trying to fetch. And if it's so, you terminate. That means that you are trying to that means that you're trying to violate the policy. That means that you're trying to execute code from what is supposed to be a data page only. But if it's not, if it's a benign thing, then you perform just one lookup of 1 byte in the page fault handler that sets the DTLB entry to valid. You flip the bit in order for this to succeed, and you immediately flip it back. So in the DTLB, the user bit allows the accesses to sail right through if you're using the data path. It's not in the ITLB, so it's if you still access it as code, it will trap. Your accesses will sail right through without causing the page fault, so long as the TLB, the DTLB doesn't get flushed. And, you know, there is a reason why these caches are there. Memory references have locality. Anytime a new lookup is done, it will trap, and the page table, you know, on the page tables, the page tables always trap. And so through this desynchronization, you're emulating the non-executable bit, using the fact that you can have them desynchronized, and using the fact that you can actually set the mirror copy of bits in the TLB to be not the same as in the page table. So this is the niftiest thing I've ever seen. If I ever do something in my career like that, I'll retire. So, you know, just think about this. Understanding that logic, and actually in the write-up, which I really suggest you read, they pay credits to the system that tried it for detecting self-modifying code. They did it for ITLB. This is more complex, and this didn't quite work. This was the Plex 86 project, at which point the PAX took the banner and carried it on to DTLB and emulating the NX bit, and they had the non-executable data pages on all architectures before the NX bit was introduced. Perfect example of how you can use the processor's internal state and internal logic for transitions to program with that. The same technique was used for a different purpose in the debugger edition, in the Oli debug edition called Oli Bone. There, it was used to make a composite trap. So we've seen composite labels. Now it's a composite trap. What Joe Stewart, the author of Oli Bone, wanted was to track unpackers, right? Unpacker writes code, then jumps to it. So you want to trap on the event that a page just written to got executed from. Unfortunately, you can't set that in the x86 flags. They only trap on, reads, writes, and accesses to pages with supervisor bit. However, if you overload your page fault handler, and in the page fault handler you decide, oh, is that the page that I just saw previously, then you can combine those and you have a composite trap. Isn't that nifty? Now, the absolute favorite of that technique, however, is not messing with a few bits here and there. Let's mess with the actual physical page frame. So let's say you have a rootkit detector that reads code, or an antivirus that reads code and matches some pattern over it. How does it get that code into its registers to do its matching? It uses, so that's not what the move does, but like move, right? Okay, so it goes through the data path. However, if you jump to that address, it goes through the code path. So you can desynchronize the DTLB and ITLB entries to point to different physical frames. And so when you're looking at this page as data, you're getting a different physical frame of innocent code. If you are looking at it, if you jump to it, however, you go to a different physical frame, and that's where the evil code lives. Hidden state. Weird machines, ladies and gentlemen. Amazing research by Sparks and Sherry Sparks and Jamie Butler. So there will be URLs when we post this. Well, so now that you have this thorough exposure to how these things work and what the hidden state might be, let's do our own.
Yes, and while we've been saying that it just handles a trap, on Intel there are in fact two different trapping mechanisms. And we're going to use the underdog that barely is used anymore except to handle very bad exceptional conditions. But first, for completeness sake, there is the traditional trap gate, which is used to handle almost all interrupts occurring on your CPU. They're just like a long jump of old. You go to a different code segment, that usually just means you transition your privilege level into the kernel, and jump to an address in there. Due to legacy reasons, it's encoded in this rather weird format inside a table called the interrupt descriptor table, which has a similar format to the GDT. And whenever an interrupt occurs, the processor just looks up the IDT in memory, which, unlike all the other tables, is not actually cached in any hidden registers, which is going to be very useful, and then pushes some parameters onto the interrupt handler stack, so that the interrupt handler looks like a regular C function you write, as opposed to other architectures where you have to read special registers somewhere. However, the issue there is, if you're just performing a long function jump and then writing to the stack, there's a whole lot of things that could go wrong. For example, the page where your page fault handler lives could also currently be marked as not present, or your stack could be broken, or you could have a stack pointer that is 0 and thereby underflows when you try to push to it. And if any of these bad things happen, Intel assumes that your operating system has a bug in it. In the old days of yore, with computers before Intel, the way would be that then a light would come on and the operator would come out and start cursing and look at it with like an oscilloscope. Because you can't really do it on a microprocessor, what they instead do is they provide you a mechanism to reload the entire CPU state from a known good configuration. And usually that known good configuration is set up to go to a special function that then dumps your kernel memory onto disk and prints a nasty message that says Linus made a bug again. And that is called a double fault. If for whatever reason the double fault doesn't work, the CPU just pulls up its reset pin and the entire CPU goes through its BIOS. Unless you set a few special tricks, in which case it doesn't.
But consider, all of this, I mean, since handling a memory error involves writing to memory, you know, there is a possibility for another fault. We're going to bounce between the page fault and the double fault, never quite reaching the triple fault. But this is going to be the clock of our machine, like the pulse up, pulse down.
Indeed, and this hardware task switching mechanism also goes back to the days of DOS when everyone was doing their own task switching and everyone was getting it slightly wrong. So Intel decided to fix it by adding their own task switching mechanism. It turned out to be like 1 cycle slower than writing it in software, so no one used it, except for this double fault handling mechanism. It just adds a similar entry to the GDT, except that it doesn't contain an address, because the address is going to be contained in that known good state that the CPU loads. And instead it contains a special kind of segment called a task state segment, which is 104 bytes long and contains almost every register that the CPU had, at least in the 386 days.
Think of it as a stash for a process to put all of its registers, and more importantly, its stacks in all 4 rings of execution. This is actually there is one task register set for Linux, one value. There is one task segment descriptor set for Linux. This is where the kernel stack lives on the 32-bit systems. When you do the system call, you switch from user stack in whatever process to the kernel stack. And this is where it actually comes from. So on newer processors, it's the manufacturer-specific registers, but it's a TSS on 32 bits.
And let's have a brief discussion here. This huge data structure, of course, is an interesting path in the CPU because that causes the CPU to fetch about 104 bytes at the same time and pass them as a more or less atomic instruction. And the Intel manual actually even says there, please, please, please don't place this across a page boundary. Because if you do, we're just going to translate the first virtual address of this TSS, because this entire task switching mechanism was before the paging system was introduced, so it all operates in virtual addresses, and then just read 104 continuous physical bytes from there. If you happen to be inside a virtual machine and place it on the last byte of a page, you might get 103 bytes that just happen to be in physical memory after you. Those could maybe belong to another virtual machine or to a hypervisor. And that made me very happy, and I was about to dance the Ode dance and think about retiring by selling Amazon's data centers back to themselves or something like that. Yeah, and thought like, yeah, sweet, here be dragons. And then I figured that we're doing this whole science thing and tried to figure it out. It turns out that Intel was very much aware of this possibility and changed the processor to read double word by double word and essentially do the virtual address translation correctly. Yeah. So there's just a sleeping manual. But manuals are also pretty cool, and while not as appealing as dragons initially, they do allow you to take it far further and actually allow you to build a Turing machine. Which in our lab tends to grow. Like you leave an Intel manual lying out and someone's going to come along and build a Turing machine out of it. It's a horrible environment. And usually when people think about building Turing machines, they try to build some complicated scheme like having a tape or something. But in fact, you don't need a whole lot to build a Turing machine. Back in the 50s, when college students didn't have access to electronics because they had to like salvage vacuum tubes from televisions or something, someone actually built a computer based on a single instruction, a decrement and branch of negative. Nowadays, it's mostly used as an educational toy or as a math statement of saying, you can have just one instruction and it's Turing complete on its own. And it's quite nice for us because it means we don't have to grab that much state from the CPU.
But you can compile C to it.
Modulo a few billion instructions. And our implementation sketch of this is going to be this. Our EIP is always going to be pointing at an invalid address. That is one that is marked not present. Thereby, we can be sure that it will never actually execute a single instruction because there is no way it can possibly fetch a valid instruction. The variables that we decrement are stack pointers in the TSS, because remember, it always pushes some bits of state about default. Even if you're doing the double fault mechanism, it pushes an error code onto the stack. which as a side effect causes the stack pointer to be decremented by 4. If that underflows, we get an error. That is, it does a double fault. If not, you load the EIP, which will be invalid again, you get another page fault. Therefore, the CPU never actually stops having interrupts and never gets around to actually scheduling an instruction, but just tries to continuously move the right bit so that maybe one day it'll find an interrupt handler that will actually do something. And in the process, it performs computation for us. And now let's quickly go over the various actors that we have involved here. We have one global descriptor table, and because the manual says it's global, we just have one and actually map it into all the different contexts that will be involved. And every single instruction that we have is going to be a TSS descriptor, which the address of which has to be in the GDT. But fortunately, we have the virtual memory context, so even though we can only, with our scheme, fit 16 descriptors into the GDT, we can in fact map an arbitrary number of them by just rewiring the virtual memory under there. And we also have a different IDT for every instruction. The IDT lives at a fixed address because you can't reload that register without actually issuing an instruction. However, you can, again, wire out the virtual memory that is living under the IDT.
So the entire memory is plastered with those tables. Normally, you have just one. But since you can switch contexts with page table translation, let's have as many as we need.
Yes, and again, these are the two parts of, or the various parts of the TSS and how we use them. Most importantly is going to be the stack pointer that we have here and the CR3, that is our current context, that we swap out just to make all the other features and tables in the processor look differently, by just having a different context where they point to different physical pages. And the reason why we split that across a page boundary is going to come, or I'm going to show in a few seconds when we step through an instruction. Initially, there's going to be a few lies in here for didactic purposes, and because we like to lie. So to give a high-level view, we have our interrupt as a rising edge of a clock. This is sort of like a rectangular clock function. At first, it's going to be saving the old state of the CPU into the TSS as it exists. Then see, okay, we have an interrupt. Let's look up where our next task is going to be. And then it loads the entire CPU state from that task. As part of that, it also loads a new CR3, so its entire view of memory is going to change. And all of the caches that Sergey mentioned, like the TLB, are going to be flushed. Then it'll attempt to push the fault info into the stack, thereby decrementing the stack pointer by 4. If you have a failure, you go to a double fault, which is going to be another entry in the IDT, pointing to another one of these TSS, going back to the beginning. If that, however, succeeds, we decrement the ESP, and then do a page fault, again, going to the beginning, which will cause the new value to be saved to memory. Let's say initially it starts off like this. We're somewhere living in kernel, have a fairly regular setup, except that we have 2 of these tasks instead of 1. And the kernel suddenly decides to jump to FFFFFFFF, which will cause a page fault.
Okay, so notice the EIP value, right? It's invalid. This is the new cool value. 41, 41, 41, 41, forget it. FFFFFFF is where it's at, because that starts the machine.
And we also have a reasonably sane stack pointer pointing somewhere in kernel memory. And so the CPU is just, it notices, okay, this is bad. Let's have a page fault. In the IDT, let's look at what the page fault is. Okay, that causes a task switch to this task pointed at in the GDT, which happens to live here. But first, let's look at the current task. There's a special register for that. Dereference it through the GDT and write that task in memory. Then it's going to look at the TSS in memory and load all of that into the CPU. As a part of that, it's also going to change the virtual memory context saved in CR3. So the entire view of what TSSs are actually living at the virtual addresses. The virtual addresses are going to be the same because they're stored in the GDT, and we only have one GDT. However, what is actually backing this storage can change radically. So now there is a new value of ESP and EIP and all that living in the TSS. This actually causes us a small implementation problem, as you always have when you're trying to build engines with Russians. Namely, there is this little bit in the GDT. That's because Intel actually tried to prevent people from looping, because they have a return mechanism, as in return from whoever caused this interrupt, and that's saved also in the TSS. And if you have a loop in there, it would just get this little circle and keep going forever. So they added a bit to prevent this. was quite hard to get around. 9 out of the 12 weeks that I spent working on this wasn't trying to get around this one bit. And after trying all the tricks, we decided, okay, let's just screw this and like shoot nukes at ducklings, namely by switching this across the page boundary. There's all these other registers that are being written to, including EAX and ECX, which we can arbitrarily control. So we're just going to make the virtual memory line up in such a way that the EAX and ECX part of the TSS also happen to be the GDT descriptor pointing to that very TSS. So the CPU sets the busy bit and saves it, then goes in and saves the state, which contains exactly the same data it just wrote, except with the busy bit cleared.
So it blows away the busy bit, but look, we're allocating this task segment descriptor over the GDT, and now we're reading and writing to it, because this is what the task switching mechanism does. Well, who says they can't do like double the job, right?
And now to go back to our instruction flow, but with slightly fixed up state. It now goes in, as you see, all of the tasks are marked as available, because as soon as it switched to them, it also immediately overwrote the busy bit with a 0. It goes in and decrements the stack pointer. That's perfectly okay. 0 is a valid stack pointer, you can write to that. And so it writes to virtual address 0, which we just mapped to go to somewhere irrelevant for now. And marks the current, then sees, okay, we still don't have a valid EIP, so let's cause another fault. Save our state back.
Tick.
This time, however, the virtual address that it saves it to might be the same, but it goes to a different physical page. So that's where we get our move from, which makes writing programs a lot easier than when you just regular decrement in branch of negative, because overflowing a 32-bit variable every time you want to do a move is kind of annoying and kind of slow. And now it notices, oh well, the stack pointer that we just loaded is 0, so we can't do this. So let's do a double fault. Load a new state, which is just another talk in our clock. And now we have yet another issue. Remember that if we have 2 double faults in a row, the Intel CPU kind of goes maniac and shoots down the entire system. And there's also, so we have to make sure that we never take 2 double faults in a row. And the other much nastier issue that also took a long time to work around is that Intel also has logic that you don't switch to yourself. So whatever the task register is, that is the index into a GDT, it has to change every time. So occasionally, we solve this by just inserting dummy instructions that live at a different TSS and then just branch back to you. It makes code execution slower, but as we're doing infinite computation per instruction anyways, we don't really care. Like, suck that, C.
Yeah, the thing is that I'm a fugitive from mathematics, so to say. And when my student comes back and tells me, you know what, there is a graph coloring problem in there. Like, yeah. Mathematics never lets you go. You never leave mathematics.
Yes. The much easier way to understand this is to actually look what is going on at the FSB, or in box, just turn on to trace all memory accesses. If you cut out the billions of accesses to various page tables in this, you just see that, and filter it to just the accesses to various stack pointers, you see very nicely that it goes through this flow of decrementing as you want it. We're running slightly low in time, so I'll hurry this up.
Skip the restrictions.
Yes, we have a few restrictions that you should talk about. The more practical applications of this, however, are that this is a nice double-strength red pill, because no publicly available simulator implements all of this correctly. My demo turns out to run on box, but that's because I needed something to debug it with. And I can't shoot down every virtual machine, because then I'll wind up without tools. But fun things happens if you do this on a virtual machine.
Yeah. So none of the simulators that we could get our hands on run this correctly. One place or another, this hardware switching task or the double faulting task, it's just
yes. Okay. And our takeaway for white hats is that you should therefore check how your tools handle such unused and weird features. For black hats is, well, if you fix this up, you can probably make a really bad day for anyone who's trying to reverse your code. And for straw hats, we have a weird machine. And because this is so fun, we're going to look at how to do this in 64-bit and see how it works on different hardware. Any questions?
The demo.
Yes. Okay.
Don't forget the demo.
Fun. I don't think we have the time for the demo.
Oh, we have the time for the demo.
Yes. If you want to have a demo, swing by and we'll talk about it.
No. Let's do it. Let's do it.
Yes.
Yes, that's how long it would take. Run it, neighbor. Run.
Okay, this is going
Yeah.
to shoot